So we're going to do one more modeling example for using integer decision variables in an optimization problem. And one last example is about embedding piecewise linear objective functions into an optimization problem by using integer decision variables. So we're going to talk about embedding piecewise linear objective functions into an optimization problem by using integer decision variables. Here's the example we're going to look at. So let's say we're producing power in two power plants, plant A and plant B. And the cost of production, the cost of power production, each one of these plants is given by these piecewise linear curves. Like for example, in plant A, up until 35 units of power that I produce in plant A, for each unit of power I produce, I incur a cost of $2. For the next 25 units of power that I produce in plant B, for each unit of power that I produce costs me $4. And for the last 40 units of power that I produce in plant A, for each unit of power that I produce, I incur a cost of $1. We have a similar power production cost in plant B. For the first 40 units of power I produce in plant B, each unit of power I produce costs me $1. For the next 20 units of power I produce in plant B, each unit of power I produce costs me $5. And for the last, let's say, 40 units of power I produce in plant B, each unit of power I produce costs me $1. In these two plants, we would like to generate a total of 100 units of power. We want to figure out how many units of power to generate in each one of these plants so that we minimize the total cost of generation while making sure that we generate 100 units of power. Okay, that is the question we're interested in. And by doing this example, we're going to see how we can embed piecewise linear objective functions into an optimization problem by using integer decision variables. Good. So we're going to define a number of decision variables, two types of decision variables. In each one of these curves, we have multiple segments. Let's call this the segment 1. Let's call this the segment 2. Let's call this the segment 3. Likewise, in this curve, we have the segment 1, segment 2, and segment 3. Our first decision variable is going to be of the form xia. Let's call xia to be, let's say xia is going to take value 1. If the generation in power plant A utilizes segment I, xia takes value 1. If generation in plant A utilizes segment I. Otherwise, xia takes value 0. For example, if we're producing 45 units of power in plant A, then our generation utilizes segment 1, and it utilizes segment 2, partially, but that's okay. But it doesn't utilize segment 3, okay? So if I'm generating, for example, 45 units of power in plant A, then I'm utilizing segment 1 and segment 2, but I'm not utilizing segment 3. So that is the meaning of our xia decision variable. Xia takes value 1 if generation in plant A utilizes segment I. Good. Let's also define another continuous variable. Let's call it yia. And that is going to be the portion of segment I utilized by the generation in plant A. Portion of segment I utilized by the generation in plant A. Okay. For example, again, if you're generating 45 units of power in plant A, in segment 1, we're utilizing 35 units. In segment 2, we're utilizing 10 units. In segment 3, we're utilizing 0 units. Okay, so those are the values. Those are the interpretation of the yia decision variables. Let's repeat again. In the cost curve for plant A, we have 3 segments. Segment 1, segment 2, segment 3. Then the decision variable xia, it's a binary decision variable. Decision variable xia takes value 1. If the generation quantity in plant A uses segment I, for example, if I'm generating 45 units of power in plant A, I'm utilizing segment 1, x1a is equal to 1. I'm utilizing segment 2, x2a is equal to 1, but I'm not utilizing segment 3, x3 is equal to 0. And our decision variable, our continuous decision variable is yia. That is the portion of segment I utilized by the generation in plant A. So if you're generating 45 units of power in plant A, And for the first segment, we're utilizing 35 units. For the second segment, we're utilizing 10 units. For the third segment, we're utilizing 0 units. So then y1a is going to be 35, y2 is going to be 10, and y3 is going to be 0. And we have the same decision variables for the plant B, xib and yib. Similar decision variables, xib and yib for plant B. Great. So then let's first think about the cost of generation in each of our plants. YIA is the amount of segment I that I utilized in plant A. So then for each unit of segment 1 that I utilize in plant A, I'm going to incur a cost of $2. For each unit of segment 2 that I utilize in plant A, I'm going to incur a cost of $4. For each unit of segment 3 I utilize in plant A, I'm going to incur a cost of $1, right? Okay, so Y1A, Y2A, and Y3A is the portion of each one of these segments that I utilize in plant A. Then for each unit of segment 1 that I utilize in plant A, I incur a cost of $2. For each unit of segment 2 I utilize in plant A, I incur a cost of $4. For each unit of segment 3 I utilize in plant A, I incur a cost of $1. So then we can write the cost of production, cost of generation in plant A as the following. For each unit of generation, for each unit of segment 1 I utilize in plant A, we're going to incur a cost of $2. This is the amount of, for each unit of generation, for each unit of segment 1 that I utilize in plant A, I'm going to incur a cost of $2. So this is the amount of segment 1 I utilize in plant A, and that's going to give me a cost of $2 for each unit. This is the amount of segment 2 that I utilize in plant A. And for each unit of segment 2 I utilize in plant A, I incur a cost of $4. And for each unit of segment 3 that I utilize in plant A, I incur a cost of $1. 2, 4, 1. That's our total generation cost in plant A. And what is the total amount of generation in plant A? Well, Y1A is the amount of segment 1 I utilize in plant A. Y2A is the amount of segment 2 I utilize in plant A. Y3 is the amount of segment 3 I utilize in plant A. This is the total amount of generation that I make in plant A. Good. And similarly, we have the similar things that we can write for plant B. For each unit of segment 1 I utilize in plant B, I incur a cost of $1. For each unit of segment 2 I utilize in plant B, I incur a cost of $5. For each unit of segment 3 I utilize in plant B, I incur a cost of $1. So let's write down the cost of generation in plant B. For each unit of generation in segment 1 in plant A, we incur a cost of $1. So Y1B is the amount of generation that we do in segment 1 in plant B. For each unit of those, we incur a cost of $1. For each unit of generation that we do in segment 2 in plant B, we incur a cost of $2. And the amount of segment 2 that we utilize in plant B is Y2B. And for each unit of generation in plant B in segment 3, we incur a cost of $3. And the amount of segment 3 that I utilize in plant B is given by Y3B. And likewise, what is the total amount of generation in plant B? That is how much we utilize the first segment, how much we utilize the second segment, and how much we utilize the third segment in plant B. Okay, good. So those are pretty basic relationships that compute the cost of generation in each one of the plants and the total amount generated in each one of the plants. So now let's try to do something a little bit more interesting. Let's try to write down the relationship between our X and Y decision variables. Let's remind ourselves, XYI takes value 1 if the generation plant A uses segment I, otherwise XIA takes value 0. XIA takes value 1 if the generation plant A utilizes segment I, and YIA is the portion of segment I utilized by the generation plant A. So if x1a is equal to 0, if the generation in plant A doesn't utilize segment 1, then the amount of segment 1 that I utilize in say, plant A has to be 0. If x1 is equal to 0, meaning that the generation in plant A does not utilize segment 1, then the amount of utilization of segment 1 in plant A has to be equal to 0. On the other hand, if x1a is equal to 1, meaning that the generation in plant A utilizes segment 1, then the amount of segment 1 that I utilize in plant A has to be at most 35. Good. So now to utilize this relationship, we're going to use a constraint that looks something like this. We're going to utilize a constraint that says the following. y1a is less than or equal to 35 times x1a. If x1 is equal to 0, the right-hand side of this constraint is going to snap to 0. That's going to force y1a to 0. If x1 is equal to 1, the right-hand side of this constraint is going to be 35. Then we're going to ensure that y1a is less than or equal to 35. But there is one more twist. If x2 is equal to 1, if x2 is equal to 1, meaning that if my generation plant A is utilizing the second segment, then I must be using segment 1 to its full extent. Let's say it again. If x2 is equal to 1, meaning that if my generation plant A is using the second segment, then the first segment must have been utilized to full extent. So if x2 is equal to 1, then y1 has to be exactly equal to 35. That's another relationship that we have, okay? Then to satisfy the third relationship, we're going to write another constraint that says y1a is greater than or equal to 35 times x2a, meaning that if x2 is equal to 1, then y1a has to be has to be at least 35. If x2a is equal to 1, then y1a has to be at least 35. But together with this constraint, y1 is at most 35 either. So then these two constraints are going to ensure that if x2 is equal to 1, y1a is going to snap to 35. Good. Again, let's remind ourselves where this relationship is coming from. If x2 is equal to 1, meaning that I'm utilizing the second segment in plant A, then I must be using the first segment to full. Then if I'm utilizing the second segment in plant A, then the utilization of the first segment has to be exactly equal to 35. So now to satisfy this relationship, we're going to use a constraint that says y1 has to be greater or equal to 35 times x2a, meaning that x2a is equal to 1. Then the right-hand side of this constraint is equal to 35, then y1 is going to be at least 35. But this constraint says y1 is at most 35. Then with these two constraints, we're going to ensure that if x2 is equal to 1, y1 is going to snap to exactly equal to 35. Good. So now let's do something similar for the second segment in plant A. If x2 is equal to 0, meaning that if we're not utilizing the second segment in plant A, then the amount of utilization of the second segment in plant A has to be 0. If x2 is equal to 1, meaning that we're utilizing the second segment in plant A, then the amount of utilization of the second segment in plant A has to be at most 25, because the length of the second segment in plant A is 25. Let's say it again. If x2 is equal to 0, meaning that we're not utilizing segment 2 in plant A, then utilization of segment 2 in plant A has to be 0. If x2 is equal to 1, meaning that we're utilizing second segment in plant A, then utilization of the second segment in plant A can be at most 25. This is the width of the second segment in plant A. To ensure to capture these two relationships, we're going to use a constraint that says y2a is less than or equal to 25 times x2a. If x2 is equal to 0, this is going to snap to 0, y2 is going to snap to 0. If x2 is equal to 1, this is going to be 25, then y2 is going to be less than or equal to 25. But also, if x3a is equal to 1, if we're utilizing the third segment in plant A, then the second segment in plant A must have been used to full capacity. If we're utilizing the third segment in plant A, Then utilization of the second segment in plant A has to be full all the way to 25. Then to ensure this constraint, we're going to also write down x2 is greater or equal to 25 times x3a. So then it ensures that if we're utilizing the third segment in plant A, if x3 is equal to 1, then utilization of the second segment has to be at least 25. But by the first constraint, utilization of the second segment can be at most 25. Then with these two constraints, if x3 is equal to 1, y2 is going to be snapping to exactly 25. Let's take care of the third constraint in segment A. If x3a is equal to 0, if we're not utilizing the third segment in plant A, then the utilization of the third segment in plant A has to be 0. On the other hand, if x3 is equal to 1, if you're utilizing the third segment in plant A, then the utilization of the third segment in plant A can be at most 40. The length of the third segment in plant A is 40. So then to capture these two constraints, we're going to write something like y3a is less than or equal to 40 times x3a. And there's no fourth segment in plant A, so we do not write a constraint that says if you utilize the fourth segment, then the third segment must have been utilized to full. We do not need to worry about that. Good. So we have these 1, 2, 3, 4, 5 constraints for plant A. We're going to write a similar type of constraints for plant B. Let's write those constraints for plant B. And they're going to be the mirror image, exactly what we did. Okay, so let's say if x1b is equal to 0. If we're not utilizing the first segment in plant B, then the amount of utilization of the first segment in plant B has to be 0. But if you're utilizing the first segment in plant B, the amount of utilization of the first segment in plant B has to be at most 40. Then to capture these two relationships, we're going to write a constraint y1b is less than or equal to 40 times x1b. But on top of that, if we're utilizing the second segment in plant B, then the first segment in plant B has to be utilized to full extent. So if you're utilizing the second segment in plant B, x2b is equal to 0, then the utilization of the first segment in plant B has to be full. So then to ensure that, we're going to write a constraint y1b is greater than or equal to 40 times x2b. That means that if the second segment is utilized in plant B, then the utilization of the first segment in plant B has to be at least 40. By the first constraint, utilization of the first segment in plant B is at most 40. These two constraints are going to ensure that if x2b is equal to 1, y1b is going to snap to 40. But let's deal with the second segment in plant B, this segment. We want to write a constraint that says, if the second segment in plant B is not utilized, if x2b is equal to 1, then the utilization of the second segment in plant B has to be 0. Sorry, let's do it again. If we're not utilizing the second segment in plant B, if x2b is equal to 0, then the utilization of the second segment in plant B has to be 0. If you're utilizing the second segment in plant B, then the utilization of the second segment in plant B is going to be at most 20 because the width of the second segment in plant B is 20. Okay? If we're not utilizing the second segment in plant B, the utilization of the second segment in plant B is 0. If you're utilizing the second segment in plant B, the utilization of the second segment in plant B has to be at most 20. So we're going to capture these two relationships by saying y2b is less than or equal to 40 times x2b. If x2b is equal to 0, y2b is going to snap to 0. If x2b is equal to 1, y2b is going to be at most 20, not 40. Okay, good. And what else? If we're utilizing the third segment in plant B, then the second segment in plant B has to be utilized in full. I cannot start utilizing the third segment before I consume the second segment in full. If x3b is equal to 1, then y2b has to be exactly equal to 20. Then our first constraint, then we're going to write a constraint that says y2b is greater or equal to 20 times x3b. Now let's take care of the third segment in plant B. If we're not utilizing third segment in plant B, then the amount of the third segment that we utilize in plant B is 0. If we're utilizing the third segment in plant B, then the amount of the third segment that we utilize in plant B can be at most 40. The length of the third segment in plant B is 40. Putting these two relationships together, we're going to write a constraint that says y3b is less than or equal to 40 times x3b. If x3b is equal to 0, this is 0, y3b is going to snap to 0. If x3b is equal to 1, then y3b is going to be less than or equal to 40. The right-hand side of this constraint is going to snap to 40. Okay, good. So this is these constraints are gonna capture the relationships between whether we utilize a certain segment or not, and how much of a certain segment we utilize. And the interesting thing again is, for example, if I utilize the third segment in plant B, I cannot start utilizing the third segment before I utilize the second segment in full. So if I utilize the third segment in plant B, then the second segment has to be utilized to full extent. Likewise over here, if I utilize the second segment in plant A, the first segment has to be utilized in full. So this is kind of the interesting relationship. Okay. So now let's put everything together. We're going to minimize the total cost of generation over all of our plants. This is the cost of generation plant A. This is the cost of generation plant B. This is the total cost of generation in all of our plants. That's what we want to minimize. The total amount of generation that we need to make over all of our plants has to be equal to at least 100. So then this plus this is the amount of generation that we make over all of our plants. That is going to be at least 100. Good. So then let's put those two objective functions and the constraint. So this is the cost of generation plant A. This is the cost of generation plant B. Add those up. That is going to be the total cost of generation. This is what we're trying to minimize in the objective function. Minimize cost of generation in plant A plus the cost of generation in plant B Good. Subject. We want to produce a total of 100 units, at least a total of 100 units over the two plants. This is the production quantity, generation quantity in plant A. This is the generation quantity in plant B. So this is the total generation quantity. Okay, we minimize the total generation cost while ensuring that we generate at least 100 units. And then we're going to write the logical relationships between all of our X and Y decision variables to make sure that if we're not utilizing the plant, if you're not utilizing a certain segment, the amount of that segment we utilize has to be 0. But if you're utilizing a certain segment, the amount of that segment we utilize has to be upper bounded by the length of the segment. So we're going to write all of these constraints. Y1A. Y1 is less than or equal to 35x1a. Y1a is greater than or equal to 35x2a. Y2a is less than or equal to 25x2a. Y3 is greater than or equal to 25x3a. Y3a is less than or equal to 40x3a. Good. These constraints. Y1b is less than or equal to 40 times x1b. Y1b is greater than or equal to 40 times x2b. Y2b is less than or equal to 20 times x2b. Y2b is greater than or equal to 20 times x3b. And lastly, Y3b is less than or equal to 40 times x3b. Great. And let's write our binary constraints. xi a is binary for every I 1, 2, 3. xib is binary for every I 1, 2, 3. yia is non-negative for every I 1, 2, 3. yib is non-negative for every I 1, 2, 3. Okay. This is how we embed a piecewise linear objective function into an optimization problem. And this idea is pretty useful. So sometimes you may deal with nonlinear objective functions. So here's a nonlinear objective function, right? It could look something like this, for example. Well, you can take any nonlinear objective function and represent as an approximate with a piecewise linear objective function. So my approximation of this nonlinear function through a piecewise linear function could look like this. So even if you have a nonlinear objective function, you could approximate it by using a piecewise linear objective function. So this idea becomes quite handy even when we're dealing with a nonlinear objective function. Of course, you can increase the number of king points to get a more faithful representation of your nonlinear objective function. So this is one little cute idea for embedding piecewise linear objective functions into an optimization problem by using integer decision variables, still writing a linear objective function and a whole bunch of linear constraints. So this is something to keep in mind.